write it, put a line down the middle. Example 2a is a perfect example of what we're going to use, either the conjugate strategy or the build the other side strategy. Now, these strategies, build the other side, factoring a difference of squares, those are the strategies you have to think when you get stuck. And what I mean by when you get stuck is when you've used all your other main strategies. Change things to sine and cos. Can you see this one's already in sine and cos? So we can't use that strategy. Then there's the strategy, get both sides to a single fraction. And you look at this one, both sides are a single fraction. I've used that one. Is there any Pythagorean theorems in this one? No. So you've used up all your strategies and you look and they're not the same and you're stuck. That's when you're going to use one of these strategies of either factoring or build the other side. In this case, when you look at everything, there's nothing you can factor. So we can't use the factoring strategy. What the build the other side strategy is it says if two things are a single fraction, you can't factor them, but they're not the same, try to build the other side. What would I need to get my denominators the same? What would I need to get my denominators the same? So this side has a denominator of sine, and this side has a denominator of 1 plus cos. So on the right side, can you see that if I added a sine theta on the bottom, I would also have to multiply the top by sine theta, because the only thing you can multiply is 1. And on this side, if I multiplied the top and bottom by 1 plus cos theta and 1 plus cos theta, at least my denominators would be the same. And that's the build the other side strategy. You decide I'm going to either make my denominators the same and see if there's something that I can do, or I'm going to make my numerators the same and see if there's something I can do. So if I do that, well, I know that both sides now have the same denominator. I'm not going to multiply that out. I'm just going to leave it in factored form. But it's nice that they're identical. I'm going to look at what happens on the top. On the right hand, sine times sine will give me sine squared. On the other side, I have to FOIL this out, 1 plus cos, 1 minus cos. Can you recognize that that's a difference of squares? So when you multiply it out, you're going to get 1 squared, which is 1, minus cos squared, which is cos squared. Okay. So we've used the build the other side strategy, and we've gotten our denominators the same. So now all we have to do is look at our numerators and say, now that we've done our denominators the same, is there anything we can do now with our numerators? Well, now I've got a cos squared and a sine squared. So it should make me think of my Pythagorean identities. Can I get 1 minus cos squared by itself? Yes. So if you think about sine squared plus cos squared equals 1. If you rearrange that and got 1 minus cos squared on the right-hand side, what would be left? Sine squared. So you can go directly to that. And you're done. So the build the other side strategy gets something the same, and then you see what else you can do. That's the build the other side strategy. Now, one of the places that you use the build the other side strategy the most are in questions like this. Remember, the rule is once you draw a line here, you can't move things from one side of the equation to the other. If you were allowed to move one side of the equation to the other, can you see at the beginning here, if you would have cross-multiplied these, you would have got 1 minus cos squared theta equals sine squared theta, which is just this. That's usually a hint to use build the other side or to use a conjugate strategy. So I'm going to show you the same proof with the conjugate strategy. First of all, what is a conjugate? A conjugate is when you have a binomial, like I have 1 minus cos here, where you write it the same with just a plus sign in the middle. You just change the sign in the middle. It'll always create a difference of squares. So if you were solving this same one with the conjugate strategy, you would work only on one side and say, I'm going to multiply by 1 plus cos theta, 1 plus cos theta, just the conjugate. And you would get to this point here, where you have sine squared theta over sine theta 1 plus cos theta. And now you would simplify instead. Sine squared over sine, they're going to cancel out. And you're left with sine theta over 1 plus cos theta, which is what we started off with originally. Okay? Now, I find that a lot of students prefer the building the other side because it's really easy to visualize, okay, I want to get my denominators the same. So I find that sometimes people use that more. But it used to be in, I don't know how many years ago, that it was not allowed to work on both sides of the equation, that you were only allowed to work on one side of the equation. So you had to start from the left and keep going until you ended on the right. And then teachers would teach their students to work on both sides, and when you were done, just erase things and move them over to the other side. And so it became kind of pointless that you weren't working on both sides, because it was just, people were, and then just transferring stuff over. So now you can prove it by working on both sides. But this is what it would look like if you started on one side, multiply by the conjugate, and simplified to get the other side. So both of those strategies are very similar, because the conjugate kind of does build the other side. It gets the same denominator, at least close, but then you cancel out the sign afterwards. So for part B here, we have 1 over 1 minus cos plus 1 over 1 plus cos equals 2 cosecant squared. So draw a line right here. So I see a cosecant squared. I know that that's related to cotangent squared. But when I look on my left side, I don't have any cotangents. So although I could change that, in this case, it makes more sense to change things to sine and cos. So if I change this side to sine, cosecant is 1 over sine, so cosecant squared will be 1 over sine squared. The 2 stays at the top. Going back to a previous strategy, can you see on the left side that I have 2 fractions? And on the right side, I have 1 fraction. So it would make sense to try and make 1 fraction on both sides. What's the common denominator? Well, this one's missing 1 plus cos theta. And this one's missing 1 minus cos theta. And at first, you might feel like, wow, this is getting really big and really messy. But it's not going to be bad. Because what's going to happen when you multiply it, you notice that that's a difference of squares on the bottom. So when you multiply out your difference of squares, you're going to get 1 minus cos squared theta. And on the top, you're going to have 1 plus cos theta plus 1 minus cos theta. Are you okay with that? Because the plus cos is going to cancel out with the minus cos. And you'll just be left with 1 plus 1. It's probably a calculator question, so you can check that. And you get 2. All right. What do we notice? We notice our numerators are the same. This is good. So now we just have to change our denominators. And can you get 1 minus cos squared by itself? Yes. It's equal to 2 sine squared. So in the olden days, you would not have this on this side. You would write 2 cosecant squared underneath here, so it was all on one side. But we're done. The left side is equal to the right side. Nice. 12a is another question.